Hello student, hi, good evening. So today we are going to discuss further. Okay, so last time we have reached up to what density of quantum, what density of state. Okay, so density of we want to exactly actually determine determine number of charge carrier. Yes, number of charge carrier, which is a function of what energy. Yes, which is a function of number of energy level. Yes, or number of quantum state. Yes, number of quantum state. So therefore, as we know very well, the each electron or each electrons and each hole. So see here, this is what my conduction band. This is my conduction band. Okay, so this is my valence band. Yes, this is my valence band. These are discrete energy level or discrete energy level or quantum state. Yes, quantum state. These are discrete energy level or quantum state. Yes, quantum state. We want to find actually this. Okay, actually this. If we are able to find this what energies, this density of state function, density of quantum state, these are what density of quantum state or density of energy state. If we are able to calculate that, then we are able to what? Then we are able to calculate the number of electrons at hole concentration. Okay, so then after that finally we are able to determine the current, and then after that we are also able to calculate the current. Then we are also able to calculate current. Okay, so therefore ultimately we are able to achieve the electrical characteristic of semiconductor device. Okay, so why we want to find what are these are nothing but density of state. What density of state. Yes, density of state function in the sense that density of state function, which implies that the density of what density of state function means what number of quantum state. Yes, number of quantum state. Yes, how many number of quantum state is there, or how many number of energy state is there. Number of energy state, number of discrete energy state. Yes, discrete energy state, number of quantum state or number of discrete energy state. Okay, so this is what density of state function. Okay, so this is either in conduction band or in valence band. Okay, so because this all thing depend upon what doping. Okay, in case of intrinsic semiconductor, both concentration are equal. Okay, so but in case of doping, if you want to make this device some doped. Okay, if you are externally doping something in this, then it become extrinsic semiconductor. Okay, so where it depends upon the doping of which type of doping you are doing in this material. Okay, that type of conductor, that type of semiconductor it will become. Okay, if you will add donor impurity, then it become n type semiconductor. If you will add what acceptor impurity, then it become p type semiconductor. Okay, so according to that we want to determine the number of what quantum state or discrete energy state. Okay, so which is a function of what this quantum state or energy state. So this is what function. So this is function of what energy. This is actually the density of state. Okay, so density of state, these are what number of quantum state, number of allowed quantum state, which is again a function of what energy. Okay, so actually our main target is to determine this is what density of state, either in conduction band or in valence band. Okay, so that's why we want to determine this. Okay, for what purpose we want to determine? Because we want what current, we want what actual main what is our main aim here, main target. What is our main target here? What is our main target? Main target is current versus voltage characteristic. Yes, for this what we need to determine first current. For current, what we need number of electron or hole. Okay, number of electron and hole. For this what we need concentration. What concentration? How much concentration is there? Okay, how much concentration is there? Concentration of charge carrier. Yes, concentration of carrier, either it is electron or hole. Yes, either it is electrons or hole, depending on which type of semiconductor it is. Okay, so then after that we are what concentration of electron and hole. For that we want to determine what number of quantum state. Okay, so this is what density of state function. Yes, first we want to determine this density of state function, which is a number of allowed quantum state. Okay, which is a function of what? Energy. It is a function of energy. Okay, after that we are able to determine concentration of charge carried. Okay, after that we are able to determine what number of electrons and hole concentration. Okay, after that we are able to determine the current. Okay, after that ultimately we are able to determine the electrical characteristic of semiconductor device. Okay, which is nothing but current versus voltage characteristic. Okay, so this is what our ultimate goal. Okay, so this is what our hierarchy. This is the hierarchy to achieve this current versus voltage characteristic. Okay, first we want to find density of state function, which is nothing but the number of what allowed quantum state. Yes, allowed quantum state either in valence band or in conduction band. Okay, either in valence band, conduction band. That depends upon which type of material it is. Is it what intrinsic material? Is it n-type semiconductor material? Is it p-type semiconductor material? If it is intrinsic semiconductor material, then both concentration is same. Okay, either you can determine the density of state in conduction band and valence band. Okay, you determine one. Okay, so other will come automatically because it is intrinsic semiconductor. If it is intrinsic semiconductor, if it is p-type semiconductor, means we are additionally what we are doping what acceptor impurity. Then in that case what we have to determine density of state in valence band. Okay, valence band. So therefore from here we can determine the number of charge carried, which is what concentration of hole, and ultimately we are able to calculate the current which is due to hole. Okay, so therefore we are able to determine the electrical characteristic of semiconductor device. Okay, if the extrinsic semiconductor is a type of what n-type semiconductor, means there is a donor impurity. Okay, donor impurity in the sense it is a n-type semiconductor, then there is no need to determine the density of state in valence band. Only you just what determine the density of state in conduction band, which is nothing but the number of allowed quantum state. Okay, so which is a function of energy. Okay, after that we are able to determine the number of electron concentration. Okay, after that we are able to determine the current, and at the end we are able to determine the electrical characteristic of semiconductor device. Okay, which is our final ultimate goal of electronic device and circuit. Okay, after that we can play with this device and we can generate a lot of application. Okay, so this is the main motto of this topic, density of state function. Okay, so now we are going to see how to determine what these allowed quantum state, how to determine the density of these allowed quantum state. Okay, allowed quantum state, which is the root cause. Okay, so this is the root cause. Once we will find this, then we are able to find all the things. Okay, Okay, so it will take some time to determine this. Okay, so this is what allowed quantum state. Okay, so now we are going to calculate the density of allowed quantum state. Okay, which is nothing but the density of function, density of state function. Okay, so this density of state function, I hope you are much clear now about this density of state function. What is this? This is nothing but number of quantum state. Number of quantum state in the sense means what? Number of discrete energy state. Number of discrete energy state where? In allowed band. That may be conduction band, that may be valence band. This depend upon what? This depend on what? Material property. Either it is p-type material or n-type material or intrinsic material. Okay, so this all things is there. Okay, so now we are going to calculate what? Allowed quantum state. Okay, allowed quantum state, density of allowed quantum state, which is further a function of what? Energy, function of energy. Now let us see. So to determine the density of allowed quantum state. Okay, in order to determine the concentration of electron and hole. Okay, so keep in mind all those things. Why we are going to calculate this? Okay, why we are going to calculate the allowed quantum state, density of allowed quantum state? Because we want to determine the concentration of electrons and hole. Okay, for that we need to calculate the number of allowed quantum state, because this quantum state or energy state is what? These are the bed, as we have seen in case of what? As we have seen in the last case. Okay, last class. Okay, you might have seen. Okay, so what is that? This is what? These are the bed where actually the electron is sitting. Okay, electron is sitting inside what? Inside the orbital. Inside the orbital is what? Inside the orbital there is energy state or quantum state. Okay, where exactly the electron is sitting. So that is the reason we are going to calculate what we are going to calculate the allowed quantum state. Okay, so allowed density of allowed quantum state. Why? Because they are sitting there what the particle is sitting actually. These are the place of particle. Okay, so now see here. Now see. So density of allowed quantum state. Density of density of allowed density of allowed quantum density of allowed quantum state. Density of allowed quantum state. Okay, so now these are density of allowed quantum state. First of all, to determine the density of allowed quantum state, we need to consider a mathematical model. Yes, we need to consider mathematical model. Through that only we are able to calculate this allowed quantum state. Okay, so for this, what we will do, first of all, see here, let us say this is my electron. Okay, so this is my electron. Yes, so now up to this means, so for whatever we have seen in the last lecture, whatever we are calculating, whatever we are drawing, that is all in two-dimensional or in one dimension. Okay, here because density of state means we need to consider a cube. Okay, we need to consider a crystal in three dimensional. Okay, we need to consider the crystal in three dimensional. Inside that we need to, okay, inside that this electron is existing. Okay, so because this is what electron, this electron is free electron. This electron free in the sense means it is in conduction band. Okay, it can freely move anywhere in the interatomic space, but it is confined within the semiconductor crystal. Yes, it is confined within the semiconductor crystal. Okay, so now see this electron, I am taking what one crystal. Okay, so I am taking what one cubic crystal. So let us see, this is my cubic crystal. Okay, so inside where, let us say here electron is here. Okay, so now these are four corner. These are my four corner. Okay, so now I am assuming that it is a infinite, it is a three dimensional, it is a three dimensional. Okay, so let us assume that it is a, this is nothing but this is a three dimensional infinite three dimensional infinite potential well. Okay, these are what k space vector. Okay, so these are k space vector in three dimension. Okay, so I am assuming what three dimension, each has what side a. Okay, so why we are taking all those things, because we need to determine density means what mass per unit volume. Okay, for that we need what, for that we need cube, we need what, we need three dimensional space. Okay, so three dimensional space, you can take any side means any length, but it is convenient for us to take the equal length. Okay, equal length. Okay, so we can, due to which we can form a cubic crystal, because in calculation it become easy for us. Okay, so it will become convenient for us if we will assume all the length equal. Okay, so in three dimensional space. Okay, so now these are, okay, I am taking it as a length a. Okay, cubic. So now I am assuming that the electron is inside what, inside the three dimensional infinite potential well. What are those infinite potential well? These are nothing but it is a crystal. Okay, it is nothing more than crystal. So this what infinite potential well. Okay, so the potential of this infinite potential well, which is a function of xyz. Okay, in three dimensional xyz. Okay, in k space vector. Here what k is like what, radius of sphere. Okay, okay, you might have seen this sphere, like this sphere. Okay, so here is a radius like this radius here it is represented by k space vector. Okay, k space vector. So therefore this is like this. Okay, so you understand this k as what, radius. Okay, radius, it is what, k radius in what, three dimensional space. Okay, space vector. Now let us see here potential of what, potential of this infinite potential well in three dimensional. Okay, x axis, y axis, z axis is equal to what, is equal to what it is equal to 0, it is equal to 0 inside what, inside the crystal, inside crystal xyz, xyz, when xyz is lying in between 0 to a, 0 to a means it is inside the, inside crystal, infinite potential well. Okay, the potential of infinite potential well is 0 inside the crystal, and it is infinite, and it is infinite otherwise. Otherwise means greater than a, greater than a means outside, outside the crystal or outside the infinite potential well. What is the potential? What is the potential? Potential is what? Potential is infinite. Okay, so inside the crystal, what is potential? Potential is what? Zero. Potential is zero. Okay, so this electron is existing inside the crystal or inside the three-dimensional infinite potential well. Okay, infinite potential well. Now now let us say we are what, we are extrapolating what, now we will extrapolate what, we will extrapolate the result of what, result of one dimensional. Okay, so now we will try to extrapolate the result of one dimensional infinite potential well, because that we have done in the past class. Okay, so whatever we have done in the, whatever we have done so far in the last class, that we have done only for one dimensional, either one dimensional or two dimensional. Okay, so in one dimensional infinite potential well, in the last class that we have seen, now we are, now we are extrapolating the result of that one dimensional infinite potential well here, which is given as what, see here, infinite potential well. Now extrapolating, let us let us let us let us extrapolate, let us extrapolate the what, extrapolate the result of what, extrapolate the result of infinite one dimensional what, one dimensional one dimensional infinite, one dimensional infinite potential well, from which we can write. Okay, so now we will extrapolate the result, whatever result we have got in the last class. Okay, so whatever we have calculated in so far. Okay, so see here we have, okay, so we can write what, so from which we can write, from which we can write like energy. See here, energy versus momentum equation, E is equal to p square by 2m. Yes, this we know very well. P is equal to what, momentum is nothing but h cut square k square divided by 2m. Okay, so now we are extrapolating this in three-dimensional space. Okay, so where this h square by 2m is same, but this k is in, this k is not in one dimensional. Okay, so now we are extrapolating this in three-dimensional space. See here, k, kx square plus ky square plus kz square. Okay, so this. Okay, so now see here, from here we can write, from here we can write what, we can write k square is equal to 2me divided by h cut square. Okay, so k square, now this k square is what, where k, this is what, k square is nothing but kx square plus ky square plus kz square. Yes, is equal to what, which is further nothing but nx square plus ny square plus nz square into pi by a whole square. Yes, these nx, ny, nz, what are these? As we have seen what from Cronin-Penny modern equation. So these are, this k value is nothing but these nx, ny, and z are integer value for this k. Okay, for this k value. Okay, so this we are getting as we have seen in the Cronin-Penny model equation. You have not seen, so you can go my this I section. Okay, you click on the I section and you will get that Cronin-Penny model equation Then from there we have what we have found from cosine function. There is one cosine function from where we are getting this pi by a. Okay, pi by a distance. This is what the distance in k space. Okay, k space varying distance. Okay, from there you can get. Okay, so this is what these are nx, ny, and z are the integer value for this k. Okay, for this k value. Now see, while we are calculating all this stuff, you will understood in coming. Okay, in coming lecture what is the meaning of this, why we are calculating all this stuff. See here, we are calculating for the purpose